You might have seen our solder printing shenanigans in episode 39 of our Project Binky series, and we've had lots of people asking for more information, and even more people telling us we're idiots. So for those of you who think we're mental, well, yes, of course. And for those of you who want to know more, well, here's how we did it. Trying to work out how to successfully wire up our dashboard given the constraints we had in terms of depth to the bulkhead, while also cognizant of not wanting a bird's nest of wiring to add to the problem, we knew what we really needed was a printed circuit board. Our biggest problem was that we had no idea about electronics save for a very abstract understanding of the notion of it. So we struck upon the idea that we might be able to essentially flatten out all the wiring by using very thin traces of solder laid down on a fiberglass board. We knew that solder and 3D printing filament have a similar melting point, so we bought the cheapest 3D printer we could find to test out our idea. We didn't film any of the testing because, quite frankly, we didn't know what to expect, but it sort of worked. We quickly figured out that a flux cord solder just made a massive mess, so we chatted to an expert and he made us a reel of 96S solder with no flux and a diameter of 1.6mm. This is a 96% tin and 4% silver mix. So why did we turn our little Tague mill into a 3D printer and not use our new 3D printer? Well, it's all about size. The 3D printer only has a bed size of 220 by 220mm, and we needed to print traces that were nearly 300mm long. And at that time, a device capable of that was way out of our budget. But we had the makings of one in the shed. All we needed was an extruder and a hot end, and a means of controlling the temperature. For the extruder, we grabbed a cheap aftermarket unit, mounted it to a custom bracket made from scraps of alley we had kicking about, and powered it with a NEMA 23 stepper motor we nicked from our rotary table. For the hot end, at first we tried this very basic version, the same as the one that was on the 3D printer. Then we made some improvements to it as we began to run into some consistency issues. A bigger heat block with a second 40-watt heater cartridge was made, but even that didn't help, so we looked for an alternative. This was the first of the replacement hot ends, which has a much better circular ceramic heating element, but even this wouldn't work as we wanted. It kept blowing the side out of the nozzle, so we ended up with this Creality hot end with a titanium throat and a tool steel half-mil hardened nozzle. We machined down the end of the main body so we could mount the assembly in the collet of the mill spindle to keep all the various operations on a common centre. We found the molten solder kept leaking in various places, so the interface between the hardened nozzle and the throat has a small PTFE washer to help keep that to a minimum. 3D printers have a heated bed for better part adhesion, and we didn't know whether we needed one, so we figured we should at least try, and use the element from an old toaster to try it before changing to some proper resistance wire. We needed to make a bed anyway because, as you can see, the T-slotted mill table is only 3 inches wide. It turns out the heated bed was unnecessary, but we didn't know that at the time. The mill control software, Mach 3, is perfectly happy controlling the 4 axes. It is indeed designed to do exactly that, but it has no facility to control the heating elements we require to turn it into a 3D printer. So we needed to figure out a way to do just that. After a little bit of research, we figured we need a PWM-controlled MOSFET switch for all the heaters, a way of actually controlling those MOSFETs, so we chose an Arduino Uno, a 200-pound Gorilla interface to increase and decrease the temperature, a switch to turn it on, and a display to show us what temperature the nozzle and bed are at. A box to put all that in was procured, and after a little light soldering, we ended up with this. So underneath this breakout board, we've got the Arduino Uno. These are the MOSFET controllers for the heater cores. This is a step-down buck converter from 24 volt, which is the power in for the heaters, down to 12 volt to power the Arduino, which is under here. There's some relays for other stuff that I'll explain later. These are the switches that turn the heaters on. There's the screen, and underneath the screen, underneath this wiring here, you've got the variable resistors that control the heater temperatures. We decided to have a 2-stage heater for both the nozzle and the bed. One which is controlled by the knob, and an extra one that we termed the boost, which is controlled by a little push button switch on the side of the box. That switch just fires those relays I mentioned and gives all of the chooch to the secondary heaters in case we needed some extra fast heating. It turns out that too was completely unnecessary. Nick then supplemented the bracket with some more brackets for me to mount my box on. So, with all the components necessary to turn our mill into a solder melting 3D printer sorted, it just needs assembling into a machine. So how did we create the G-code for Mach 3 to run the printer? Well, it started with Nick drawing out the layout in a graphics program called Inkscape. This went through dozens of revisions as our understanding got enhanced, and we then broke it down into two sections, front and back. This is the back of the board. This 2D representation got saved as a DXF file and imported into Fusion 360, where I gave the 2D lines some depth by extruding them to a height of 0.2mm and a width of 0.5mm. This model was then exported as an STL file suitable for 3D printing slicing software. We tried a few, but this one called Slicer allowed us to fiddle the figures and lie to the software about the filament diameter. This was necessary to get the solder feed rate correct and took some trial and error. Further fettling was done with the motor tuning set up in Mach 3. After letting the slicing software do its thing, you end up with the G-code. I tidied it all up in Excel, removing unused and spurious lines and tweaking the Z-axis height and some of the speeds to end up with exactly what we need. So, fire up the printer, set your Z height to about 28/100ths of a millimeter using a feeler gauge, set it to go, walk off and have a cup of tea. Well, that was the plan anyway. This happened time and time again with no rhyme nor reason. At first, the leaking was identified and fixed, but this just kept happening. No matter the upgrades to the hot end, the fiddling with the settings, for no apparent reason it would just stop, or blurt out, or lose the Z height and scrape the board, or lose X and or the Y position by a fraction or sometimes more. We just couldn't understand why it wouldn't lay down with any consistency. We spent months chasing our tails, pulling our hair out and generally dreaming of burning the place to the ground. We very nearly packed it all in.
Nope, lost them both again. What the fuck is going on? Might be something in the code.
Nope, it was nothing to do with the code, Nick, or the hardware, or the plan. It was all sound. Early on in the process, the venerable old Taig lost its power supply. The mill is produced over the pond and is therefore a 110 volt machine. This transformer steps down from our 240 volt to the Septic's 110. It died a death and took with it this. This takes the 110 volt and steps it down again to 36 volts to power the mill's stepper motors. It was all ancient and well used, so we replaced it with something more modern and thought nothing of it. But that should have been our first clue. Soon afterwards, the stepper motor driver board failed, but again we chalked that down to its mileage and age, and we figured that the power supply fault might have just pushed it over the edge. So we replaced that too, and carried on struggling. Over the following months, the replacement power supply expired, and so did the replacement stepper driver board. And indeed, one of the stepper motors itself died. Something heinous was going on, but we just couldn't figure out what. All the wasted time, all the grey hairs, and this pile of useless solder scraps were all the fault of this. It was pure chance that we found it. Our old school battery charger with the needle type charge indicator was on, and the landlord was using the big ass pressure washer out in the yard plugged into one of our sockets. Nick happened to be drying some paint with the hot air gun, and out of the corner of his eye he noticed the needle on the battery charger dropped to 0 when he switched the gun on. How singular, he mused. So we did a little digging and found out that our entire electrical socket run was one long spur and not a ring main. When any big load went on, the voltage dropped from around 240 volt, like you'd expect, to little more than 210. When the voltage drops, the amps increase to compensate, and that's what was blowing up all our stuff. It also led to the inconsistency because the stepper motors would randomly miss steps and hang up. All our woes we traced to the mains power. Once we figured that out and took steps to rectify the situation, we rebuilt the computer once again. We installed individual stepper drivers powered by individual power supplies, got some nice big fans in there, and started all over again. Just to top it all off, a little later on, the PC's hard drive failed, taking everything with it, including the operating system, the Mac 3 software, and almost every single code for every single milling or printing job we've ever done. Don't forget to back your stuff up, kids. Still, after all that, when it worked brilliantly, and the entire back of the main cluster board was printed in less than an hour. To finish off, for all you ASMR folks, here's pretty much the whole print run for the back of the board in its entirety. Thanks for watching.